Hello there. It's been a while since you last heard from me, and I stumbled across this integral right here. Now, this integral quite possibly has the most amazing result I've ever seen from integration in just all full stop. Like, it's genuinely an insane result. So definitely stick around till the end to see that. Okay, so getting into it then. Now, the first thing that I think when I look at this integral is that how can we sort of deal with that cos of 2x squared, okay? Because we've got this Gaussian here, this e to the negative x squared, but then we've got this cos of 2x squared sort of attached to it on the side. Now, the first thing that I think of is that this can be written, this cos of 2x squared, can be written as the real part of e to the power of 2ix squared, where I is, of course, the imaginary constant. Now, using Euler's formula, this can be written as cos of 2x squared plus I sine 2x squared. As we only care about the cos of 2x squared, we can say, okay, we want the real part of e to the power of 2ix squared. Right, the cos of 2x squared represents the real part, the sine of 2x squared represents the imaginary part. So then, substituting this into our integral, we get the integral of e to the negative x squared times the real part of e to the power of 2ix squared dx from negative infinity to infinity. We can just bring that real part outside of the integral. We don't need it inside the integral. So now we get something like this, and then using the laws of exponents and adding those two powers, as well as factoring out the negative x squared from it, we are going to get negative x squared times 1 minus 2i in the exponent there. Now I want us to focus on this 1 minus 2i. So if I bring that to the front, we can see that we've actually got a Gaussian integral of the general type, where we've got e to the power of negative ax squared, where a is just some constant, some number. In this case, it's 1 minus 2i. Okay, we actually already know the result to this integral, the general Gaussian, and it's equal to root pi over a, where a is that number in front of the negative, in front of the x squared there. However, it is only true when the real part of that number is greater than 0, because if it was less than 0, then you would actually just get positive x squared in the exponent there, and it would be an entirely different integral. And so checking the real part of 1 minus 2i, well, we see it's just 1, which is, of course, greater than 0. So that's okay, all checks out. We can apply this result here. So the real part of this integral is just nothing other than the real part of the square root of pi over 1 minus 2i, where that 1 minus 2i there is the a next to the x squared, as we discussed before. Now, here's the thing. We've technically got an answer. The real part of root pi over 1 minus 2i is a number, right? It does just give you a number. So technically this would be, I guess, okay as an answer, but I'm not happy with it. I want to find what the actual result is simplified. Okay, so we're going to be simplifying the real part of root pi over 1 minus 2i. So to start, I'm going to bring out that root pi there from inside of the square root, and then it's our job to simplify this fraction, this 1 over 1 minus 2i. And to do that, to simplify a complex number like this, you have to times the top and the bottom by the complex conjugate, okay? So that's just the identical, that's just an exact copy of the complex number, but instead of a minus, we've got a plus, or if you had a plus, you would instead have a minus in the middle there. So up top, we're just going to have 1 plus 2i. And then in the bottom there, okay, well, we've got 1 times 1 just gives you 1. We've got 1 times positive 2i, that gives you plus 2i. We've got minus 2i times 1, that gives you minus 2i. And then we've got minus 2i times positive 2i, and that gives you 4, because you've got the minus 2 times the 2, which gives you minus 4. But then you've got I times I, which gives you minus 1. So in overall, you've got 4 there, which means that our overall result is 1 plus 2i over 5. So that's what we're going to put inside the square root. And just to simplify this a bit more, I'm going to bring that 5 out and join it with that pi. And then we need to go ahead and actually work out what the square root of 1 plus 2i is. This is the difficult bit. So I find it easier to approach problems like this using the exponential form of the complex number. So we're going to try and rewrite the square root of 1 plus 2i as, some re to the I theta, where r is a number, theta is, of course, a number as well, and I is the imaginary constant. Finding r is fairly straightforward. It's just the magnitude of the complex number itself. So the magnitude of 1 plus 2i is just going to be the square root of 1 plus the square root of 2, which gives you 5 overall. Finding the value of that theta is also fairly straightforward. It's just the argument of the complex number. So it's the argument of 1 plus 2i, which is the same thing as arctan, or the inverse tan of 2 over 1, which just gives you arctan of 2. So instead of r e to the I theta, we've actually got 5e to the I arctan of 2, which when we square root, because we've got the square root of 1 plus 2i, gives you root 5e to the I arctan of 2, all divided by 2. Now it's our job to actually find what on earth this number actually is, what the square root of 5 e to the I over 2 arctan of 2 is. What on earth does this simplify to? Now let's not forget, we're only interested in the real part of this complex number. So the first thing that we're going to do is we're going to use Euler's formula again and rewrite this as root 5 cosine of a half arctan of 2 plus I sine a half arctan of 2, which it appears I actually forgot to write down the half here, but it's supposed to be there. Anyway, we can cancel out the I sine of half arctan of 2 because that is the imaginary part of this complex number. We only care about the real part, so the sine part has gone. So then we're just left with simplifying root 5 cos of a half arctan of 2. Now, what on earth does this evaluate to, and how do we even evaluate it? Well, the first thing might be to consider this cos of a half arctan of 2, right? That's the bit that's tripping us up. Now, that is going to be difficult. So instead, we could have a look at what cos of a half arctan of x simplifies to, and then just replace the x with a 2 when it comes to it. Now, the way you tackle this is you start by doing a substitution. We're going to let y equal the half arctan of x. So we've actually got cos of y here. Next, we're going to rearrange our substitution for x. So that's timesing up by the 2 and then doing tangent on both sides. We get tan of 2y equals x, and now we need to find what cos of y is based on this, based on what tan of 2y is. We start by drawing a right triangle with an angle of 2y and then filling in the side. So we've currently got tan of 2y being x, and tan is opposite over adjacent, so we can label the opposite x and we can label the adjacent 1. Now, using Pythagoras, that makes the hypotenuse the square root of 1 plus x squared. And as cos is adjacent over hypotenuse, we can say that cos of the angle, so cos of 2y, is 1 over the square root of 1 plus x squared. So we've got cos of 2y, but we want cos of y. So what are we going to do? Well, we're going to use the double angle formula. So if you recall, cos of 2 theta, where theta is just our angle here, that equals 2 cos squared of theta minus 1. It equals, there's a few others as well, but this is the one we're going to use because we can relate cos of y here directly to what we have managed to get so far. So replacing theta with y and actually applying the double angle formula, we get 2 cos squared of y minus 1 equals 1 over root 1 plus x squared, which, when we rearrange for cos squared of y, gives us 1 over 2 root 1 plus x squared plus a half, which we now take the square root of to get cos of y in terms of x. Now, this is exactly what we wanted. However, we did not want x involved in the equation. That was just sort of a template that we were creating. We actually wanted, if we would call arctan of 2, not arctan of x. So going back then and replacing the x's with 2's, we end up with something that looks like this. Now, I've also put in the plus or minus in front of the square root. Sorry, I missed that the first time round. If you were screaming at the video, then I do apologize. But yes, we've got plus or minus. So the square root of 1 over 2 times the square root of 1 plus 2 squared plus a half, which simplifies to 1 over 2 root 5 plus a half, which then simplifies to this, which, if you neaten up and rationalize, the denominator will give you this, plus or minus the square root of root 5 plus 5 over 10. So now we know exactly what cos of y is equal to. Now, Why did we actually want to know this? Why did we want cos of y? Well, if we go back, we were wanting to simplify cos of a half arctan of 2, which we've now got. That is going to be, cos of a half arctan of 2 is just going to be root 5 plus 5 over 10, which if we times by that root 5 from earlier, that was outside of the the simplification, then we get this, plus or minus the square root of 5 times the square root of the square root of 5 plus 5 over 10. It is a mouthful to say. But why did we even want this? Well, we wanted this because we were trying to simplify the square root of 1 plus 2i, which we've now got. The square root of 1 plus 2i can be shown to be written as plus or minus the square root of 5 plus 5 root 5 over 10 if you simplify it, which turns into plus or minus the square root of 1 plus root 5 over 2. Now that we've managed to simplify the square root of 1 plus 2i, we can go all the way back to the beginning where we got our initial result, if you will, to the integral, the real part of root pi over 5 times the square root of 1 plus 2i. And instead of the square root of 1 plus 2i, we can write in plus or minus the square root of 1 plus root 5 over 2. Now, what does it actually mean to find the real part of this number? Well, we've got that plus or minus there. Now, that minus is going to end up inside of the square root. And, of course, we can't have the negative inside of the square root because that will lead to imaginary numbers again. So if we're finding the real part of this, then we're actually only concerned about the positive branch of the square root of 1 plus root 5 over 2, not the negative, which hopefully some eagle-eyed among you will have spotted that 1 plus root 5 over 2 is the golden ratio. That is nothing other than phi itself, the golden ratio. And so what we can actually do is we can write this as the square root of pi over 5 times the square root of phi, which when you bring it together gives you the square root of pi phi over 5. Try saying that 30 times. Who knew there was so much rhyming in maths? But yes, this is our answer. This is a very beautiful result to an otherwise deceivingly difficult looking integral. And so actually writing it out, then we get the integral from negative infinity to infinity of e to the power of negative x squared cos of 2x squared dx gives us the square root of pi times phi over 5. A golden integral. Amazing.